There's no audio, but that might be just an issue with YouTube. So you may want to put the CC titles on.
Yeah. Oh, yeah. I think it's just a kind of a tune in the background, actually.
Okay,
So it'd be more important
perfect.
for the
Okay,
other
cool.
one.
Just wanted to make sure.
Yeah, I know there's just a bit of a tune in the background, but yeah, I think the video explains everything. But yeah, thanks. Okay. Now I just need to get to the. Oh, sorry. Okay. Sorry. Sorry, I'm not fully au fait with Zoom. My apologies. Okay, so I think that there we go. Okay, so we're back to the presentation now, Kayla.
Yep, I think you might just have to go full screen just to get rid of the top bar, but you should be good to go.
Yeah, it's okay. Yeah. Right. Okay. Right. Okay. So that's I said that. So that's the fast and the slow cycles explained. And then I suppose, well, what's the issue? So we have additional levels of CO2 into the atmosphere. That's actually 50%, not 42% in that video. It's a bit out of date. Essentially, this is the issue is the greenhouse effect. So we have solar radiation arriving at the Earth's atmosphere. A certain amount would be reflected back into space. So white will reflect 99% of the solar energy, but most passes through the atmosphere. A small amount will be absorbed, but most will reach the Earth's surface, similar to the solar energy passing through the panes of glass in the greenhouse. Most of the energy is absorbed by the plants on the ground within that. And then what's released back is infrared or heat energy. And of course, this is where the panes of the glass on the greenhouse make the greenhouse warmer. And whereas in the atmosphere, we have greenhouse gases which do this. Now, this is critical. Without greenhouse gases, we would have the physicists have done the calculation. No greenhouse gases on Earth would make it very chilly. We'd be an average surface temperature of minus 18 degrees Celsius. Okay, so this is where greenhouse gases make life possible on planet Earth. But of course, as we've seen since the Industrial Revolution, we've increased that by about 50%. So instead of one pane of glass, we now have 1.5 panes of glass, and we're kind of galloping towards double glazing. So obviously more heat trapped means more energy in Earth's weather systems, and we're all familiar now with all the extremes of climate, the droughts, snow in Saudi Arabia, burning heat in Iceland, and so on. So this is disrupting the Earth's weather system. So this is one is the greenhouse effect, whereby we have a habitable planet, and climate change is the fact that because we're putting all these extra heat trapping gases, we're thickening the panes of glasses on the greenhouse. Everything's getting a bit wilder. So here again, this is just another couple of graphics. We have this is since 1850. Essentially, there's been an exponential increase in the consumption of greenhouse gases, and we're now at about 427 parts per million. Just on the graph on the right hand side, there's a couple of you may have heard of the idea of climate justice. So we have the issue here is that historically the UK started first, Europe and America, and of course China now has taken up the slack in terms of burning of fossil fuels because they're making lots of our stuff. Whereas the continents that are actually worst affected, Africa and parts of Asia, have contributed least. So that's where this idea comes from. Just again, I wanted to give you a visual to hold on to, just to kind of get into your memory better than I might be able to do. So I'm just going to show you a quick 1 minute clips. Essentially, it's this here on the bottom left. It's just a time lapse of CO2 emissions since the dawn of the Industrial Revolution in 1750. Okay, so what you can see here, okay, it starts off in 1750. You can see the UK there, so that's where the Industrial Revolution started. They started using coal instead of wood and charcoal to do all of that, carry out industrial processes. Started off a couple of million metric tons of carbon being burned and emitted into the atmosphere. On the left, of course, is the legend. So the deeper the color, the more the emissions. And essentially what you're going to see here is the Earth lights up like a Christmas tree as time progresses and the Industrial Revolution and manufacturing spreads across the globe. So we have here the year, we have the increase in levels of emissions. So progressing relatively slowly. Okay, then we see things tick up once it spreads into Germany, Northern Europe, France. There's an increase, and then it really kicks in from 1850. You get Eastern North America coming in, industrializing, using coal as the main power source. And then, of course, to the end of the 19th century, they discovered oil, started using oil, and you can see the effects. Now, this is okay. It's just going to keep going. There was a bit of a downtick during the period of the Second World War for obvious reasons, but then things picked up a pace since then. And this needs a bit of updating. It will terminate in 2008, I think. Okay, but you can see the effect. Okay, and it was at that point in time, it was 8.2 billion tons. 2025, we're now over 50 billion tons. So that's what I'm saying. It's exponential increase. This is what we're talking about. So obviously that's more heat trapping gases, and this is the issue. Okay, I just wanted to do one other quick video as well, just to show you again. It's just I'll ask Kayla, can you see that? Is that the one we want? And we probably don't have any. And do you have any sound?
Yep, we have some sound.
We have sound on this one. Excellent.
Yep,
okay,
should be good.
So, excellent, thank you. Right. Okay, so what we're going to see here, this is just NASA satellite. So you can measure, because carbon dioxide absorbs energy at, I think it's 4.26 micrometers. You can use spectrometric radiation from satellites to measure where the CO2 is being emitted on the planet. Okay, just a word, this is a NASA satellite. Is going to be defunded by Trump. I think there's a conglomerate or a consortium trying to come together to keep this satellite going, but this might go dark if that happens. Up until present, this is still running. And again, it's the same principle. So the legend, it's a model of CO2 emissions, and the intensity of the color indicates higher levels of CO2 emissions. And what we're going to see, and you can also see here, obviously, there's the vortices. So, these high concentrations are being released from industrialized Europe and China and Japan and so on. But then they're swirling because obviously the Earth is spinning. So you have the vortices in the upper atmosphere swirling and mixing those gases until you get an even concentration throughout the Earth's atmosphere. And what we see is very interesting. It's very impressive. You'll see these high concentrations. Then as spring comes, the leaves, there's a lot of vegetation in the northern hemisphere. The trees and the vegetation will come into leaf, and it will start using that carbon dioxide. And you will see the colors will drop, they will diminish, almost back down to background levels. But then, of course, autumn. So after spring comes summer, comes autumn, the leaves will fall, and then the trees will become dormant again, and then the coloration will increase. But anyway, listen, I will after that explanation, I'll let Bill explain everything.
At NASA's Goddard Space Flight Center. What you're looking at is a supercomputer model of carbon dioxide levels.
Okay. Right. And we'll go back to the presentation. And back at the presentation, Kayla.
Yes, you're good to go.
All good. Cool. Thank you. Right. Okay. So obviously that's that's very intense coloration, but I suppose the hopeful thing is that you can see the power of healthy ecosystems. You know, the health of the forests are, the healthier those peatlands are. You can see their capacity to diminish the amount of CO2 in the atmosphere. So I think that's a good takeaway from that, and it's a nice visualization of what's going on. So just to kind of conclude on this section, I'll get rid of this scan protection now. I don't know if you're seeing that. Okay, nice. Solicited ads. Current situation is we have about just over 3,000 billion. A gigaton is a billion tons. 3,000 tons, billion tons of carbon dioxide in the atmosphere today. The level is about 427 parts per million. That is the highest for the last 14 million years. And that is up from pre-industrial revolution. And again, looking at the records, that's for the 10,000 years before that, it's up from 280 parts per million. And that's essentially as a result of the fact that just over 2.6 trillion tons of carbon dioxide have been emitted since 1850. And just another thing to register is that, you know, every 2 billion tons of extra carbon being burned, which is equivalent to 7.8 million tons of a billion tons of CO2, results in a part per million increase. Okay, right. Just wanted to ask at this point, does that make sense? We kind of got the gist here, and then we wanted to get on to, you know, how does this relate to agriculture and, you know, carbon credits and everything. So is that okay, everyone? Any questions? I'm going to take that silence as a yes, so I'll continue from here. Okay, so we need to look then, so now that you have a better picture of what's going on in terms of this, of carbon pollution, we need to look at the relevant greenhouse gases for agriculture. So we have the main ones, carbon dioxide, methane, and nitrous oxide. So we do a lot of work with peatlands. Obviously, peatlands are a big source of carbon dioxide. Peat is all undecomposed carbon. When it's dry, it degrades and it's released as carbon dioxide. Methane comes from cattle, essentially. So this is the enteric fermentation, where cattle chew the cud, the bacteria generate methane, and this is where this comes from. And nitrous oxide is the other main greenhouse gas in agriculture, and this is essentially fertilizer use. When you put artificial fertilizer on the ground, part of a small percentage, maybe 1 to 2.5% of the nitrates, will be converted to nitric acid, HNO3. And just to mention at this point, Bastiaan will go into it in a bit more detail after. He'll explain this better than I can. But everything is, maybe I'm skipping, I'm jumping ahead to the next slides. Yeah, okay, here, this is the next slide. Yeah, so you can see those are the three I just mentioned. The other three greenhouse gases are essentially industrial. So they have nothing to do with agriculture. They're not natural. They are just found as a result of industry. So just looking at the carbon dioxide, methane, nitrous oxide, everything. So, we need to get an overall picture of what are the emissions, what are the sinks, and what is, in terms of carbon credits, we need to know how much is emitted from a carbon footprint perspective. And if we have methane emissions and nitrous oxide emissions and carbon dioxide, that's apples and pears and oranges. So to compare them all, we need like for like, we need a euro, we need a dollar conversion. So that conversion factor is essentially the global warming potential. So in other words, the amount of heat, infrared heat, the 1 ton of carbon dioxide can trap additional heat that can trap in the atmosphere, and everything is converted to that. So we can take methane is approximately 24 tons. So 1 ton of methane is equivalent to about 24 tons of carbon dioxide. So I don't know if you've seen maybe on the landfills, you can have flares when you have anoxic, low oxygen conditions. When the biological matter degrades, you get methane release. If you flare that off, it will convert it to CO2, obviously, but that massively, by 95% reduces the global warming potential. Turn it from methane to carbon dioxide has that effect. Nitrous oxide is in and around 300 tons. Okay, so even though we might only be talking about a few kilos per field, when you do the mass, you do the multiplication, that's quite a significant warming effect. Okay, just quick bit of context. First of all, Europe, and then comparing that to Ireland. You can see here, I'm not going to go through the thing in detail, but you can just see on the right-hand side, essentially the average emissions from greenhouse gas emissions from Europe is of just under 11%. Okay, so this is what we're dealing with. Ireland, this is just the total greenhouse gas emissions per country, needs to be updated. So Ireland, if you can find it there, we're just in and around 60 million tons. I'll just make the point that at the moment, that does not include LULUCF emissions. So LULUCF is land use change, and forestry emissions, so it doesn't include peatlands. So peatlands, when they come in, it could be anything from an additional 6 to 10 million tons. But anyway, that will come into effect, I think, next year or the following year, but just to make that point. And then in the graph on the right-hand side, the other way we can represent emissions, although we're very low in terms of, compared to Germany, we're very, very small. In terms of per capita emissions, so in other words, how many tons are emitted per average person living in Ireland, we're way up there. We're just behind Luxembourg. So this is that. So why is this? Well, let's just come on to, what's the difference between agricultural emissions in Ireland and in Europe. So you can see that it hasn't really changed from 1990 to 2022. It's in and around, it was 36 million tons, and now it's about 38 million tons in the last few years. And as I said, these are the gases. And then if we're looking at the break, where is it coming from? Essentially, it's cattle. And then the agricultural soils is essentially nitrous oxides. So when you put artificial fertilizer, as I explained, you get this conversion of a portion of this to nitrous oxide, and this is that contributor. This doesn't include, as I said, the emissions from peatland soils. So peatland soils are not in here. When peatland soils degrade, you get CO2. So this is missing from that graph. Okay, so just a few definitions. So I think, greenhouse gas, I think it's already explained. Essentially, it's a gas. It's like the panes of glass in the greenhouse. certain gases can trap that infrared heat radiation that would otherwise escape back into space and would have the Earth a very cold place indeed. We have obviously sources. So, I'm a source now. We're all sources. We're breathing out CO2. The car, when you switch it on, if you're burning petrol, a house being heated by coal, etc. These are all sources of greenhouse gases. A sink is anything that takes that out of the atmosphere. So a tree, a healthy bog, for example, our sinks. Reservoirs are important stores of carbon. So obviously we have forests are important stores, but peatlands are way better, So 3%, peatlands cover, let's say, because they accumulate continuously and they have thousands of tons per hectare. 3% of the Earth's surface is covered by peatland, but it has between 2 and 3 times the amount of carbon stored in all of the world's forests, which covers more than 30% of the world's land surface. And then, of course, we also have stores of carbon in the ocean. Emissions, obviously, is, whenever you burn a fuel, that's a greenhouse gas emission. Remove it when that plant uses that CO2 and fixes it as carbon, produces food. This is removal. And then the global warming potential, I'm going to leave that up to Bastiaan to explain because he does it better than me. Right. Okay, so let's come on to carbon footprinting because this is where carbon credits come in. Okay, so essentially we need to do something about this. And the better organizations, the better companies, the governments that are more in tune to these things, the tool that would use is a carbon footprint. So before you can start to take action, you want to show what it is that you've done. So a carbon footprint is essentially, so I'll just go through the process. We could all do it for ourselves now. So the way we would do it is, let's say we would identify, okay, I drive a petrol car. You can measure how much fuel you use over the course of the year. Okay. There is an emission factor. So when you burn a liter of petrol, it's equivalent to so much CO2 equivalent emissions. If we're heating our house with wood or with coal or with peat, same thing. We can say we burnt a ton of coal or a ton of peat or whatever, and this is our emissions. So these are our direct emissions that we use to move around and that we use to heat our buildings. And the businesses can do the same thing. Okay, so this is the direct carbon emissions. So we call these scope 1. There is a standard for this, and this is what's required in terms of peatland credits. Everything has to be done to what's called the ISO, is the International Standard Organization 14064 standard. So you measure your scope 1 emissions. The next thing you would look at is your scope 2. So this is your electricity usage. So obviously we all need power for our homes and so on, and our businesses. But the thing is here, they're classed as indirect emissions because most of us don't produce our own electricity. We just consume it. And of course, that varies from country to country. The more renewable energy there is in the mix, the lower. So every kilowatt hour, if you look at your electricity bill from ESB or whoever, you can see there's a conversion factor. The back says 1 kilowatt hour equals, and I think last time I looked, it was maybe 300 grams of CO2 per kilowatt hour or something like this. So same thing, how much electricity have we used in kilowatts? And we can make the conversion. And then lastly, and this is the trickiest, but most relevant to farming, is scope 3, because the agri-food industries, obviously for them, they control their fuel usage and their transportation, organize efficient transportation routes to go and collect milk, etc. They can buy green electricity, do things, but the tricky stuff is the indirect emissions. So they're trying to get their farmers to reduce. Essentially, farmers are scope 3 for agri-food industries. So, they're undertaking various measures to encourage more environmentally friendly carbon practices. So to reduce the carbon footprint of milk and so on. And then from our point of view, again, just coming back to the example of an individual, that would include, what kind of food am I eating? I'm eating lots of meat. I'm eating more vegetables. I'm eating a lot of fish. How do I dispose of my waste? Do I put it all in landfill, or do I recycle it? Do I compost it, and so on? So these essentially the contractors and suppliers. So these are scope 3. These are tricky, but for the companies that are looking at these things, scope 1 and 2 is easy. Scope 3 is what they're turning their attention to. And then this is just a graphic of what I was just explaining. So it's essentially carbon footprint is, as an individual, what am I responsible for in terms of tons of CO2 emissions? So, for example, and as we saw, the average for Ireland is about 13 tons per individual. Okay, credits come in when an organization then wants to offset this. So let's say as an individual, I wanted to say, right, I want to do my bit for the planet and the environment and biodiversity and nature, etc. And I can actually, a credit is I have 13 tons. I want 13 tons of credit equivalent. So I will pay someone else to plant trees, to restore peatland, maybe to erect a wind farm or something to offset this. So we can do that at an individual level, at an organizational level for a region. And also, you may have heard of life cycle analysis. So this is what the companies, the agri-food companies are doing. They want to know for every liter of milk that they produce or every kilogram of beef that's processed and put on the market, what is the carbon footprint of this? Okay, and I think, yeah, this is just, again, a graphic of what I explained already, I think. So, yeah, that's where we are. Okay, just to finish up on this section, before I hand you over to Bastiaan's capable hands, just a few terms that you may have heard that knocking around that you may not have understood. So, climate neutral, carbon neutral. So the aim, if we're looking at the international agreements on greenhouse gas emissions, the aim is that the Earth is carbon neutral by 2050. Okay, and what that means, of course, is that whatever we emit in terms of fuel consumption, whatever is offset by more trees, by more healthy peat bogs, taking up the excess and so on. So carbon neutral, net zero is a similar idea. We need to get to the situation where, you know, that's balanced out. So in other words, we're not putting any additional carbon dioxide into the atmosphere, which will allow the Earth to kind of start regulating itself again. And then carbon positive would be even further, whereby, you know, we're actually whatever we're emitting is being outweighed. So in terms of additional forest. So hard to think of carbon positive examples, but there are carbon positive countries. So just think of all those countries with big areas of forest and maybe lower levels of industrial activity, maybe Guyana and stuff in, I think, Costa Rica, in Latin America, the Congo. There's a lot more forest taking up a lot more carbon than is being generated by all the activities of the people in those countries. CO2 equivalent, I mentioned already, and also carbon offsetting. So we have our carbon footprint, and then we do the offsetting. And for example, there's an organization that we do work with, a construction company. They have done their carbon footprint. It's about 20,000 tons of CO2 equivalent per year, which they're emitting as a result of their activities in Ireland. So they purchase that. So they purchase credits to the equivalent of 20,000 tons, tree planting, renewable energy, and so on in Africa and Asia. But they would really like to do that in Ireland. So in terms of the peat, we talk about, you know, stacked income opportunities, you know, from carbon credits from the peatland standard, and then what we can grow with paludiculture. This is one of the things we're talking about. Okay, this is just a graphic. Again, it's the slides will be available, but, you know, just to make the key point, because, you know, there's the thing about climate justice. So, you know, if companies are emitting huge amounts of CO2 and then they buy and plant trees in another country, which in the past has involved displacing farmers from those areas and planting a load of eucalyptus, which is a complete disaster and extremely unjust. This is not the way to go. So this is essentially buying us time for us to reduce emissions, substitute renewable energies for fossil fuels, and to try and minimize the effect, to try and lower the extremity, you know, to minimize the extremities as a result of climate change. Okay, and just lastly, and then I will hand you over to Bastiaan. How do we do this? So there's a few principles here. And what you do is you will, in terms of carbon credits, there's the hierarchy of energy management that must be applied. Okay, so just as you can see on the right, there's only just 80% of all our emissions come from just 57 companies. So those organizations should not be allowed to purchase any carbon credits. They just need to stop generating, you know, they need to stop exploiting fossil fuels. Okay. So that would be, so they need to reduce their energy demand. So this is the approach: reduce the energy demand. So you're familiar with, you know, movement sensors, light sensors in buildings, energy efficient technologies. So I'm here in an office, and, you know, we've got LEDs, which use, I think, 10% of the energy of previous types of light bulbs. The next step you need to look at is renewable energy. So can you get solar, can you get wind energy into the energy mix that you're consuming as an organization? And then, and only then, when you have done that, should you qualify for carbon to be able to buy carbon credits. And I said, this organization we work with, they have done all of this. They do all of these things. They have a detailed carbon footprint, and consequently, they qualify to use these things. Okay, so I think, look, that's probably enough from me. I will hand you over to Bastiaan at that stage if there's no more questions. And thanks
Yeah.
very much for listening to me. I hope you
Sorry,
found that
I will
informative.
share from my own screen just to
Yeah, sure. I'll stop
so
sharing
you can
and
ask some questions while I
take
put
over.
it up on the screen, and then
Yeah.
there's some time for people to ask things.
Does anybody have any questions?
Maybe in the chat. You got anything going on? Nothing is.
If not, that's okay.
It means everyone
We need more
understood everything you
questions
said.
later. Just put them in
that's
chat.
Yes. Can we make it big? Sorry. Yes. Okay. Right. Doug, thanks for that. I will be talking about carbon farming and specifically about how that will look like on a farm. So which measures that you can take. When we're talking about carbon farming, there are two areas that we can look at. Those are the carbon sinks and the carbon sources. You want to increase the carbon sinks, so the carbon sinks will draw carbon out of the atmosphere and put them somewhere safe. We call this carbon sequestration. Or you can look at the carbon sources, so everything like we talked, the enteric fermentation, nitrous oxide, and oxidizing, degrading peatlands, they all emit greenhouse gases, and we want to minimize those emissions as far as we can. So they're called avoided emissions. Now, for the sequestrations, there are on, let's say, land-based carbon sequestration comes basically in the category of soil carbon and woody biomass. So we're talking about forests, we're talking about hedgerows, planting forests, and for the soil carbon, we can be talking about grasslands, because grass is a very, very effective crop, which will put a lot of carbon into the ground when it's properly managed. And we're talking about healthy peatlands. The peatlands are not very productive. However, any carbon that they do put into the ground stays there because of the wet conditions. In a healthy peatland would be completely wet. And in those wet conditions, anything that gets put into the ground stays there. It doesn't afterwards oxidize anymore. And when we're talking about avoiding emissions, well, the big player, obviously, as Doug already mentioned, is the enteric fermentation. So the methane belches from cattle and other kinds of livestock, as well as manure management. So this is almost 30 megatons of CO2 equivalents per year. It's the biggie. I don't see how we can. I don't know if we can address that like very, very quickly. But anyway, it's a really big thing. The other major player that Doug already talked about is the nitrous oxide emissions from fertilizer application. So this is more than 5 megatons of CO2, 5 billion tons of CO2 equivalents per year. And then something that's not included in the national accounting now, but which is really, really high, is the oxidation of drained peatlands. So drained peatlands, they degrade, and the carbon that the peat is made of gets oxidized and goes up into the atmosphere as CO2. On just peat grasslands in Ireland, this is about 4 megatons of CO2, and this is all CO2. It's not CO2 equivalents, it's real CO2 per year. And so when you think about the national greenhouse gas budget of Ireland is 60 megatons. So this is more than between 6 and 7% of all the CO2 that we're emitting comes from drained peatland. So it's really, really significant. And it's one that we can address quite effectively and easily. We'll talk much more about that in a few slides' time. And then there's some minor sources, and it's maybe surprising that the fuel that you spend, with the tractor and everything on the farm, it's really, really a marginal contribution to the total emissions from farming. Other small contributions are liming, so the calcium carbonate that lime consists of, part of that carbon from carbonate gets emitted into the air when it gets in contact with the acid soil. And then urea in itself has a bit of CO2 in the molecular structure, which gets released when it reacts in the soil and then frees up the nitrogen, but also the CO2. Okay, so just a little bit about carbon credits and CO2 equivalents, because it is a term that we are talking about all the time. and I don't know how well it's understood. So first of all, a carbon credit is basically just 1 ton of CO2 equivalents that is either sequestered, so taken out of the atmosphere and put somewhere safe, or avoided, in that you emit less than you would otherwise emit. And we need to talk about CO2 equivalents because there are these three main agricultural greenhouse gases. So they are methane, nitrous oxide, and of course, CO2. We're taking CO2 as the standard, and to calculate the effect on the climate of the other two, we use their heat retention, so how effective they warm up the planet, but also how long they stay in the atmosphere. Because methane, for example, it is a very, very strong warming effect. However, it's very reactive. It gets eaten up by microorganisms, it reacts with oxygen in the air, and so the methane that we emit today in 20, 30 years won't be anything of that left. So all have disappeared. So you need to, sorry. So when you're talking about the global warming potential over the next 50 years, this is the standard measurement that people are generally using to compare one greenhouse gas to the other. You are thinking about how much of the how much of the methane that you're emitting today is still going to be there in 50 years. So this gets taken into account. And as a result, like I said, methane is very strongly warming, but because it stays in the atmosphere for a short time, the global warming potential is 28 times that of CO2. So 1 ton of methane is worth 28 tons of CO2. Nitrous oxide, it's very strongly warming also, but it stays in the atmosphere for a long time, even longer than CO2. And so it has a global warming potential of 265, so that's almost 300 times as much as CO2. And therefore, even though we're not emitting that much nitrous oxide really, it still has a really strong effect. And because of this large factor, you see that it emits 5 CO2 equivalent tons, whereas the real amount is a couple hundred kilos maybe only. I'm sorry, a couple hundred kilos only. Okay, and then so finally, and this is something that really applies only to peat, there is dissolved organic carbon, C, and particulate organic carbon. These get washed out from the peat. So one gives the peat gives the water that tea-like color, and the other is just little bits of peat that are flowing away. They are carbon, and CO2 is carbon, but it also is oxygen. So every 1 ton of carbon combines with 2.7 tons of oxygen and makes 3.7 tons of CO2. So when you're talking about DOC, you're like, oh, but it turns into CO2. So why is it so much higher? It's because 1 ton of carbon is 3.7 tons of CO2. So it's important to keep in mind that carbon and CO2 are two different things when it comes to the climate. Okay, let's move on. I don't know why it's not moving. There we go. Okay. Yeah, so let's talk a little bit about carbon sequestration. Like I said, carbon sequestration means removing greenhouse gases from the atmosphere. The only way we can really do that is by taking CO2 out of the atmosphere. Now, obviously, we can pump it small and store it in underground caves. This is not something that we're going to talk about today. I'm not a particularly big fan of that system. It doesn't seem very safe to me, but okay. What we are talking about is perfectly safe, and it is all to do with storing CO2 in plants and through plants in the soil. And so what you always want to keep in mind is if you want to sequester as much carbon as you can, is you must optimize your plant productivity, so make the life of your plants the best it can be. This is something that any farmer wants, so that's very happy coincidence for us. And then what you also want is to make sure that once it gets into the soil, it stays in the soil. And so there are a couple of ways in which carbon gets released from the soil. In peat, for example, it's when you drain the water and let the oxygen in. But in other kinds of soil, every time that you disturb the soil, you will allow more oxygen into small places and more carbon will get emitted. And that's why a land that's been plowed year after year after year after year they are generally very, very poor in carbon. So if you see the figure here, carbon gets stored in stems and leaves and in live roots. And when these die off, they turn into what we call litter. So it can either be above ground litter of the stems and leaves or below ground litter of the roots. The roots also emit root exudates, which they use to free up nutrients, but they disappear within days to weeks. So they're not really counting for much. The litter that the roots deposit into the soil gets eaten up by the soil floor, so earthworms, bacteria, everything like that. Part of it gets re-emitted as CO2, but part of it also gets turned into what we call humus. So that is either particular organic matter or organic matter that's bound to the soil minerals. And that's the organic matter that has a much longer residence time, between 1 and 10 years. So the litter, the root exudates, they don't really count. They get eaten immediately. The litter stays for 1 year. So it's also not a really stable source of carbon, but the soil organic carbon is more stable and stays there for a long time. And so you can use this to really build up the stores of carbon in your soil. It is complicated because if you, for example, take a measure, well, I'm getting ahead of myself. We'll talk about that a little bit more later. The other big ways are to store it in living biomass. So that is mainly trees. I mean, smaller, more fragile plants, they die, and leaves, they get deposited and eaten up, as we just saw, and turn into CO2. But living biomass trees, they stay standing, and they can stay standing depending on your forest for 100 years or even more, depending on the tree species. And then you can turn trees into dead biomass, such as timber, and this is also something that can potentially have a very, very long lifetime. So just planting a forest will have its maximum, but if you take away the timber and put it into a house, you keep that CO2 out of the atmosphere for even longer. And then finally, we have something that we call transformed biomass. This is biochar or charcoal. This is chemically condensed and it becomes very, very stable. And so you can use hedge clippings, for example, char them, and then use them as a soil improver. You spread them out and they will stay there for 1,000 years. So essentially, this is truly forever sequestered carbon, or at least at the time span that we're talking about. Okay, and so what can you do on your farm? Like I said, you can plant forest. So this means standing biomass. You can also coppice forest for biochar to have a true sequestration of the carbon forever. And then you can keep doing that and keep sequestering carbon. Or you can you can plant forest for timber. And so this is also a relatively long-term removal of CO2 from the atmosphere. To just see here, this graph, I won't bother you with the details, but it comes down to about 8 tons of CO2 that is being taken up by the atmosphere on average over the lifetime of a forest. Because you see, when a forest starts growing, it goes slow. So those first years, barely anything gets taken up. But at some point, the trees reach their production peak, and then they reach their production maximum. So over, let's say, 100 years, you can take up about 8 tons of CO2 per year. If you improve your hedgerow,
sorry, Bastiaan, just per hectare, just make sure, So
per hectare, yes.
You just left
absolutely.
that out, yeah. So for a hectare of forest, you'll take up this. And then also, if I can just add, depending on the type of forest, you can take up more, So different types of woodland will sequester. But I think the maximum for Irish forest, say mature oak forest, is about 500 tons of carbon per hectare. Yeah.
Yeah. Okay. Yeah. Standing in total, you mean, in a mature forest?
Yeah. Exactly. Yeah.
And so the other way is to plant or improve your hedgerows. There's a lot of gappy hedgerows. So whenever you plant a tree there, that tree is going to take up carbon while it grows. And then once it reaches its maximum size, it's going to stop taking up carbon, but it's still going to be stored carbon there. It's going to be a carbon reservoir. About 3 tons of CO2 equivalents per kilometer of hedgerow can be taken up every year. And the way you improve your hedgerows, if it's already full, is to trim it less frequently. You let it grow a bit wider, you let it grow a bit taller, and this makes sense financially as well, because you don't have to pay the guy to come over that frequently. And then afterwards, when you have the clippings, there'll be more woody biomass in there, which you could turn potentially into charcoal and then spread in your land. So this, by doing this, increasing the size of the tree and then using the chippings for charcoal, you can sequester about 3 tons per kilometer, which is approximately the same value per hectare, by the way, as for the forest. You can convert cropland to grassland. So as I said, plowing really disturbs the soil and makes the carbon come out as CO2. And so when you convert that to grassland, you not only plant a crop that puts down a lot of carbon into the soil, but you also stop disturbing it so much. And so you can, for a relatively long time, put down about 4 tons of CO2 per hectare every year. And so it's quite an effective measure. And then finally, there's improving your grassland management. So generally, grassland isn't disturbed that much. It's not plowed, but you can improve the productivity of your plant, make the grass grow better. You can do this by optimizing your fertilization. You can do this by planting multi-species swards, because the other kinds of let's say the chicory and the plantain, they will have roots that go deeper into the soil where grass normally doesn't deposit any carbon. You can decrease grazing intensity or implement rotational grazing if that decreases grazing intensity, because the main idea is to have more leaves on the grass. More leaves mean more area to capture the sun and take up CO2. So and they will have more energy than to put down into the roots. And then finally, you can apply slurry and farmyard manure instead of artificial fertilizer, because they are both contain quite a lot of carbon, and that carbon partly gets emitted, but partly it also gets deposited as soil organic carbon. Oh, sorry. And so, okay, you can do this for just the carbon credits, but carbon credits are not the only thing that will benefit you when you are applying these measures, and especially the higher soil organic matter is very beneficial for the farmer, because it improves soil structure. So that means you'll have less compaction, less erosion, you'll have better infiltration of the water, and so that means that also your water supplies, they will build up faster after a long period of drought. You have a much higher nutrient availability. So you can see this here in the graph that when soil is fertilized with manure and mineral nitrogen, the nitrogen availability then gets disproportionately higher. So it has more effect than just the added amount of soil organic matter. That's great, but you also, with that, increase soil life, and that increases the nitrogen availability for your plant. So it's a virtuous cycle, let's say. And then finally, you increase the water holding capacity. So this is just a graph I made based on some data. There's about 120,000 liter of water that can get stored inside the soil. So not in a wet soil, just in a normal soil that doesn't feel super wet. You can store 120,000 liters of water per hectare for every percent of soil organic carbon. And that can mean, as you can see in the graph, hopefully you'll understand it, but if not, take it from me, that it means that here the higher organic matter soil will not suffer any drought stress here. And for the blue marks, you will not have any drought stress at all throughout the whole year. Whereas without the extra organic matter, you will have that drought stress in June. And so these are the most productive months. This is also when you have the higher chance for drought. And so it really makes a difference to have that 2 extra weeks of full growth can really make a difference for the amount of grass that you produce. Obviously, optimum fertilization increases the productivity of your plants, and that increases the amount of carbon that they put down to the ground. About close between 6.5 and 7 is optimal, because you optimize the availability of both so phosphorus, the micronutrients, and nitrogen and potassium. And then so if you go a little bit higher, the micronutrients become limiting, and if you go too low, the nitrogen becomes limiting. So this is really the golden, the golden zone for max productivity, and therefore for max uh, carbon storage. So it's a knife that cuts on both sides. Multi-species swords, they have additional benefits because they have lower fertilizer requirements, and they have, therefore, because you can put lower fertilizer, they will have much lower nitrous oxide emissions. And even if you do want to fertilize at the same rates, you will still have lower nitrous oxide emissions. And then finally, because of the deeply rooting plants, the resistance against drought is much higher because they can just get water from deeper in the soil than grass can. Hedgerows and agroforestry, they provide shelter and shade for animals, which is great, really improves their health. I've heard that it can advance the time of lambing for sheep by about a week in spring. And then as well, the trees and the leaves, they give extra opportunity for browsing for extra nutrients. A lot of our farmers, they report that whenever they let the cattle into the field, the first thing they'll do is go to the hedgerow and eat from the leaves there. And these extra nutrients, the different kinds of food, it just contribute to overall health and will reduce veterinary costs as well. And also
just one thing.
Yeah.
Oh, sorry, Bastiaan. Sorry to interrupt. Just also if we're talking about carbon footprinting, and you're talking about the fertilizers, there's also when you're doing the footprint on the farm, there's the embodied energy in the fertilizer when it's being manufactured. I think it's equivalent to about 5 tons of CO2 equivalent or thereabouts. So obviously less fertilizer equals less embodied energy. So that's another thing, but more from the carbon footprint inside rather than co-benefits, just to throw that in there.
Yeah, definitely. Yeah, that's a good point. Yeah, and so as I was about to say, some trees, depending on which trees, but they have like extra medical medical properties. So willow leaves, for example, have been proven to decrease the worm load in sheep or in lambs. So that's another advantage that you might use to your benefit. And then finally, and not insignificantly, all these measures, they will benefit biodiversity. It's not something that immediately translates into money, but a lot of our farmers, at least, they're very, very happy when they see the wild ducks return or see a little bit more birds in the hedgerows. And so all of the measures that we've been talking about, planting forest, increasing the hedgerows that will produce more fruit when they're trimmed less frequently, and so there'll be more birds, more insects, just more life on your farm because you are giving them more places to live. Okay, and so that's carbon sequestration. Let's talk a little bit about avoided emissions.
Can I ask a quick question?
Yeah, sure. Oh, yeah, I forget that.
Dell had a quick question. Do you have any figures for paludiculture farming?
I think maybe, Kayla, would it make more sense if Bastiaan just covers the next section and then
Yep,
we
cool.
come on to that
I just wanted to
question?
make sure if it was
No.
if it was the
Sure.
timeliness of it.
Yeah,
But
no,
Dell,
I
I
think
have your
that will
question
follow on.
pinned, so we'll look at it at the end.
Cool. No, that will follow on neatly from what Bastiaan's about to present.
Okay,
Yeah,
cool.
maybe whoever asked the question can take the time to clarify if they are talking about carbon sequestration or other kinds of figures. But okay, we're talking
Thank
about
you.
peatland now, so it'll come up maybe. Let's see after. Right. So avoided emissions, I think I've made it clear, but it doesn't hurt to just reiterate. It means decreasing the greenhouse gas emissions that you are causing by managing the land or that are just occurring on your land. And so one really good way to avoid some emissions is by using protected urea. About 71% lower nitrous oxide emissions using protected urea compared to CAN, calcium ammonium nitrate. And this is simply because the nitrogen gets released slowly and the plants don't have this big kick of nitrogen, which is too much for them to all take up at once. And then you have leftover nitrogen in the soil, and the bacteria, they get to work on it, and it gets emitted as nitrous oxide. So when it gets released more slowly, plants are able to just use it more efficiently and make sure that there's not this excess of nitrogen in the soil. But the big thing is water table management on peatland, which is the star of our show, really. So why are there any emissions on peatlands? Peatlands emit a lot of CO2 when they're drained. And drainage is so ubiquitous because it has been absolutely key for conventional farming practices on peatland. When you drain a peatland, the first thing that happens is that the soil will settle and shrink. And this is really important because it makes the soil firm. It allows you to go there. It allows cattle to walk there without getting up to their knees into the blubber. I'm sorry, the blubber, that's Dutch. Without getting into their knees in the muck. It allows your tractor to drive there. And also, peat starts oxidizing when you take the water away. And that releases the nutrients that are trapped in the peat. There's a nice graph here. It shows the nitrogen uptake on peat grasslands, and these are unfertilized peat grasslands. So there's, depending on the drainage, so the more you drain, the more peat oxidizes, and so the more nitrogen gets released. And so in a moderately drained peatland, you would have about 300 kilos of nitrogen becoming available for the crop. So that's, I mean, that's far above what you're allowed to put out on the field right now. So
Yeah,
it's really great for. Sorry.
Oh yeah, just a quick one. Just made me. Do you want to explain, peat and the fact that it's essentially all carbon? In a normal field, all the grass will decompose, but peat is essentially part of that is accumulated. Maybe.
Didn't I already cover that a little bit? I mean, I can do it. Like you're talking about how peat comes to life, how it exists.
Yeah, no, just the fact that it's all carbon, and it's just, we cover the mineral side, but just to clarify the difference, because you're talking about it degrading and oxidizing, and just obviously the fundamental thing there is it's basically it's plant material, and maybe in a typical bog or fen, instead of all of the leaf decomposing, it's maybe 15 to 20% will accumulate. So basically, when it's drained, the bacteria, the bugs come and finish the job, so to speak. So that's the source. So that's what I was meaning.
Very well put. I don't think I have anything to add there.
Yeah,
I hope that's clear.
Yeah. So a lot of pure carbon with some minerals, basically. That's essentially peat, and this is why it's so different to, because you were saying with mineral soils, it's only a small percentage up to maximum of maybe 8% in a really high stockage in a mineral soil, whereas peat soil is all carbon. So when it degrades, it's just pure carbon into the air. Sorry, just
it's between well, depending on the peat, but can be just 100% organic matter. So when it oxidizes, there's nothing left, and that's exactly what happens. So you drain it, and oxygen comes in, and it starts eating the organic matter. But because peat is all organic matter, it disappears. And first of all, there's a lot of CO2 that's being released up into the air, but that CO2 is what your soil used to be. And so you get something that's called peat wastage. The shrinkage initially is just the water getting out and the peat becoming a little bit more firm. But after that process is completed, the oxidation just eats away the peat until there's nothing left. And so in a number of farms that we've seen, peat has degraded to about 10 centimeters. And then underneath that peat is the impermeable layer that allowed the peat to form in the first place. So this is a really thick, hard layer of marl, and it's very, very hard to work. It's very, very hard to drain, and so it's going to make farming a real struggle. Just here, for you to see, this is a relationship between the water table. So here we have the water table. It's very deeply drained here, 1 meter drainage, 60 centimeters drainage, and here the water is at the surface. And so this is the amount of CO2 that you emit. And so the exact figures don't really matter, but something that we're talking about all the time is that every 10 centimeters of drainage emit approximately 5 tons of CO2 per year per hectare. And so when you have something that's drained maybe half a meter, that's almost 25 tons of CO2 that's being emitted every year. And so this is really, really, really significant. And the combination of that story is that we get to that 4 megatons, 4 billion tons of CO2 equivalents that are being emitted
Four, four
annually.
million tons. 4 million tons, Bastian. 4 million, not billion.
Oh, sorry.
Yeah, sorry,
Oh,
4
it's
million.
million, is it?
Yeah,
Oh,
yeah,
okay,
yeah,
sorry. I
yeah,
get confused
yeah.
between the mega and the
Yeah, that's
and
it.
the giga.
We're not that bad. And then also, if I could just add, you see in the side that Bastian is presenting. So I think the average for Irish deep drained fertile peat grasslands is about 28.5 tons of CO2 equivalent per hectare per year. And that's mainly CO2, as Bastian was explaining. The figure there is talking about 60 tons. So when you plow it, because of what Bastian was saying, you're introducing even more oxygen and peat. So you're really burning it up. So that's why you get the 60 tons. And we have very little of that. I think there's only about 10,000 hectares of arable peatland in Ireland, but in the UK, this is like their bread basket. They produce a lot of wheat, potatoes, and vegetables, and they're losing their fields at a rate of 2 to 5 centimeters a year, to the point where it's shrinking so quickly. Of course, when it hits, as Bastian was explaining, once it gets down to the water, and this is very low lying, it's near the coast. When it hits the water table, there will be a point where the energy to pump out the water, it's no longer worthwhile. And I think that's also a situation kind of being reached in Holland where you're actually below sea level. Yeah.
Yeah, well, we're having even more fun with peat in the Netherlands. Yeah, most peatlands, when the peatlands formed, they were at sea level, right? Every once in a while, the sea came in, but generally was desalified by the rain. But when we started to first mine the peat and then drain the peat, I think at some places we're now 10 meters below sea level, and that's still sinking. Despite our best efforts to keep the water table high, the land is still going down. And yeah, when you see then that the sea level is rising, and it gets pretty scary. If you're ever in the Netherlands, go to a sea dike and see where people below, how deep they are below the surface of the sea, and you will understand that we are really, really concerned about our peatlands sitting even deeper down. Okay, I think we can move on. So let's talk about what happens when you try to undo the drainage. When you block the drain, the water doesn't flow away freely anymore, and it's gonna fill up the drain. This is something that happens within the span of a year, easily. And when that happens, the water comes back up, and all that oxidation, so everything here, all the bad stuff, but also all the good stuff, kind of gets reversed fairly quickly. So the CO2 emissions, they go down, but sorry, I'm getting ahead of myself. Apologies. CO2 is going to go down, but something that also happens is that methane emissions will start to increase because of very, very wet soil. In these conditions with low oxygen, easily degradable carbon sources, they get transformed into methane. And so there is a kind of sweet spot where you are draining enough to really have a big impact on the CO2, sorry, where you are raising the water table enough to have a really big impact on the CO2, but you're not raising it that much that you also get a high methane emission. And so this depends on how much methane can be emitted from the soil. A very rich soil generally would emit more methane. Poor soils would emit much less methane. So if you can see here on the right, the blue line is the CO2 equivalence, so the sum of the methane and the CO2. And so you see, you keep going down, until you get at about 20 centimeters drainage, and then the methane starts weighing in. But because the CO2 is still going down, the optimum lies at about 5 centimeters drainage. So this would be a completely fully rewetted soil. That's the best from a CO2 and a greenhouse gas perspective. If you have a much richer soil that would emit more methane, it'd be better to go down to about 20 because the methane emissions just explode up when you are bringing the water table higher. And so there are figures for what you can expect. And so yeah, we can help you choose, let's say, the best approach for the climate and for the land that you have. So as I already erroneously started to talk about, when you re-wet your field, the good things disappear with the batching. So CO2 emissions almost stop, but also you're going to have to deal with the lower burying capacity, the reduced excess, uh, less nutrients are being released, and a lot of crops that you might be growing there at the moment. So let's say ryegrass, for example, they won't do very well on very wet soils. So, but all is not lost, because even, like I said, every 10 centimeters saves us 5 tons of CO2. So even if you increase the water table only by a small bit, you still have the opportunity to really have a positive climate impact. And if you look at this graph here, this is a graph uh, which displays the drainage depth, so the groundwater table, and the penetration resistance. That's how firm the soil is. And so let's say there's a critical limit where people consider you shouldn't have your cattle out anymore because you're going to trample the grass too much. You're going to get into, let's say, the right side of the photograph there. That is at about 40 to 50 centimeters. You should be good. You won't reach that critical limit and you can still have your cattle out. And so if you go from a very deeply drained soil, let's say 70 to 60 centimeters, of which peat grasslands in Ireland, 20% approximately is estimated to be at that drainage depth, and you go to between 40 and 50 centimeters, which is something that also Chagas advises at like as the best drainage depth for peatlands, you save approximately almost 10 tons of CO2 per hectare per year. So this is a really, really substantial. And let's say if you would do that for all the deeply drained peat grassland in Ireland, you would be saving between 6 and 7 thousand tons of CO2 per year. So that's close to 1 million. It's about 1% of the national budget. It's not gonna save the world, but it's still significant enough that we think that this is really a no-brainer to do. This is just free, free climate benefit. Essentially, the farmer won't suffer any problems. And so, okay, is that all you should be doing? Well, it depends on what you want. In terms of climate, re-wetting more is better. Wetter is almost always better until you get to the methane emissions. But in principle, the higher the water table, the lower your greenhouse gas emissions. And so there are alternative ways to be using your grassland. You can have hay or summer grazing, so you mow it once a year. This is something that many farmers are already doing on kind of these cut over grasslands. And as you see, the water table goes up and down a little bit. So you would have maybe in summer between 25 and 30 centimeters drainage. And if there's plenty of grass growing there, that gives a little bit of extra structure to your land. And so you could mow it, even if it's re-wetted to a relatively high water table. And then there's another almost 10, it's a little bit less because of the methane, but there's almost an additional 10 tons of CO2 for every hectare to be gained there. Another thing that we can think about is bulrush. This uses a water table depth really at the surface. It can be used to make construction material. Well, a guest speaker has spoken extensively about this. He's really got the whole pipeline figured out, and we're slowly hoping to see some movement there in the coming years. So this is definitely an interesting option for somebody who with a lot of bravery. And then another thing, I'm definitely not giving a full list of paludiculture crops here, but cranberries, they use a water table depth between 10 and 20 centimeters would be good for them. They can be an interesting cash crop. And so this is another option that you could have if you really want to maximize your climate benefit. Okay, so I think that's enough for the moment about peatlands. I just wanted to address like a couple of terms that you might run into if you were talking to other people, maybe about carbon credits and carbon offsetting. So they're overlapping somewhat, but not completely. I'll try and explain them as best as I can. So there's business as usual versus change of management. Business as usual is what you're doing now. This is basically you don't care about the climate and you just keep farming the way you've always been farming, completely never minding about emissions. Change of management is making an active decision to do make a change for, in this context anyway, for the betterment of the climate. Additionality means that that change of management that you are doing is motivated not by external factors, but really by any kind of financial reward that you would get for your carbon credits. I think I'm explaining this a little bit the wrong way around. The point is, if you want to get payments for carbon credits, which is definitely an option, and which we will talk about in the next webinar extensively. I won't address it here too much, how that works, but it exists, just let's keep it at that. Additionality means that those payments are critical for you to implement that change of management. So for example, if you would already have a forestry grant, you have the forest planted, you cannot then also get carbon credit payments for the carbon that's stored in the living biomass, because you are doing it anyway, right? The carbon credit payments, they don't factor into you planting that forest. Double payments are a little bit similar here, and so it's kind of the same. If, for example, you have an acre scheme and you're getting paid for something, then you cannot also get paid for that same measure for carbon credits. Baseline, very closely related to business as usual. It is the situation as it is now, but you need to understand about baseline that the baseline isn't just today. It is what would naturally happen between now and, let's say, the next 10 years. Now, for example, if you lower your applications of fertilizer, this will lower your nitrous oxide emissions. But can you then get carbon credits for that because you're avoiding emissions? Well, that depends, because you might simply be writing out less chemical fertilizer because it has become so expensive. You might be just financially motivated to apply fertilizer in a different way, and then carbon credits won't apply. So baseline is not something that is necessarily what you did this year, but also something that, given the changing conditions, you would be expected to do next year. And so this, again, it comes down to the additionality. Changes that you were going to do anyway for financial reasons, they are not, they cannot be counted for carbon credits. The baseline also means that it needs to be very well established what's your current situation. So when we're talking about peatlands, for example, you need to see how degraded the peat is, how much CO2 you're emitting now, and then after you block a drain, how much CO2 are you emitting then? In other words, did it actually make a positive impact? Because if it didn't make a positive impact, potentially, depending on the scheme, you cannot get paid carbon credits. Direct and proxy-based monitoring, they're very, very important. Direct monitoring is when you're going and you are actually looking at the CO2, or you're actually looking at the carbon that you sequester in your soil. It can mean that you're measuring the width of the tree. Well, maybe that's also proxy. It can be that you're taking a soil sample and looking at the carbon, the soil organic carbon in there. Proxy-based monitoring is when you're looking at something else and calculating the CO2 emissions or other kinds of emissions from that metric. So, for example, in peatlands, we use water tables. Deeply drained peats emit a lot, shallow drained peats emit little, and so any change in the water table can be used to calculate a change in emissions, and that change in emissions can then be used to calculate carbon credits. Action-based payments versus result-based payments, they mean that, for example, I'm just sticking on the peatland, that you get paid simply for blocking your drain, or you get paid for the effect that you have on the water table. There are different schemes right now. Some will, not necessarily in Ireland, but there are other countries, there are schemes where just the fact that you're blocking the drain gives you a payment, whereas in other places you really need to demonstrate then the rise in water table. And there are also schemes where you get a little bit for simply blocking the drain, and then you get more for successful raising of the water table. This is very, very closely related to ex ante versus ex post. I think in many cases it's the same. It's not 100% the same. Ex ante just means payment upfront, and ex post after you show that has been successful. And here as well, there can be a mixture. So you can get some money up front, and you can get the bonus afterwards when it's successful, for example. And then just a minor thing that's coming up a lot during our trainings is the fairness of the whole system. So I don't know if I've managed to convey it, but you will always get paid based on the impact you make. And the worse you're doing right now in terms of climate and emissions, the more significant the impact is that you could make. So if you have a peatland that's drained down to 70 centimeters and you want to re-wet it all the way to the surface, that is a huge change. And that avoids a lot of emissions. And there are potentially very high payments attached to that. Whereas if you are already having a nice high water table because you like a little bit more of biodiverse grassland, and then you raise it fully just for the carbon credits, you will potentially get less. So there's a bit of a reverse incentive here to have a really, really bad baseline. Don't go and drain your fields now because you just heard this. There are some mitigation measures in the carbon standards. So there's a certain disqualifying criteria, like if you have just recently cut the peat, you cannot then say, okay, now I'm going to restore the peatland and go back. So there needs to be like a 5-year gap between doing something very, very destructive and getting paid for restoring it. Other ways of mitigating this difference is biodiversity credits and payments for ecosystem services. They are to some extent incorporated into the Irish peatland standard. So if you have a good biodiversity rating and if you're providing ecosystem services, for example, water storage is a very important ecosystem service for peatlands, they count to the quality and the value of your carbon credits. So just having bare peat but very wet will not grant you a very high price for your carbon credit. So it's something that always comes up. I figured I really needed to mention it. But I think that is all for me. And we'll open the floor to questions.
Can you leave that there, Bastiaan? If you leave the last slide there, we'll just come on to that because there's been a few questions which really relate to that. So I think if you can just leave the last slide up and then we come up. Yeah, and then we just come up. So just to elaborate on what Bastiaan was saying. So yeah, there is this perverse incentive, but there is a time thing that will cut it off. So if you went and stripped your bog now, then that's within the timeline, so you wouldn't be up for credits. But and it's also just to answer the couple of questions came in from Del Greco. Sorry, Kayla, I'm cutting out your question reading
You're fine.
Contribution there, but maybe there is some more after. So it was just about paludiculture farming and then the figures for the value of the carbon credit. So we're working, obviously, our aim with our current project and the one that we're about to start is to get the first, because no individual farmer, unless they're really huge, would have enough carbon credits to supply to a buyer. So we're looking to do the first group farmer project. That would be of interest. So essentially, it's equivalent probably to about 20 hectares of change in water level on peat grasslands. But what so anyway, consequently working closely with Peatland Finance Ireland, who are in charge of this standard, and essentially the operating principle, because the question was, what's the figure of the value of the carbon credit on the open market and projections? So essentially their operating criteria and ours, which we'd already come to independently, was it really needs to be 100 euros a ton of CO2 equivalent to be interesting. And of course, the way you do this is it's not just carbon, because if you wanted just carbon, you could just plant a load of eucalypts or spruce, no biodiversity, acidified water, no people, no farming, and where you go. So Leitrim would be perfect for this. Not the way we want to go. So what we're saying is to get that higher value, We want it should be carbon, and it's the biodiversity, because when you raise the water table, you also bring back a host of biodiversity. Dry peat, you have a lot of wetland species there, and they're essentially inactivated by the fact that it's dried. When they get wet, they come back again. And then also, as Bastiaan mentioned, there's the ecosystem services of the water storage. And then also you cut off, there's all of that pollution effect of the carbon and the nitrates. That's also addressed. And then, of course, the other thing is that we're really pushing, and that's kind of what we're all about, is that should give more income to the smaller farmers, or any farmers, but maybe smaller farmers in particular, because that's who we work with more, to keep them in business. So as I said, the PFI, peatland fire zone, that's what they're aiming for. So about 100 euro at the moment. It's probably more 30 euros a ton, but 100 euros a ton is kind of what we're aiming at. And then also to add, there is a compulsory. There's like it's the emission trading scheme. These would be for companies that emit a lot of CO2 equivalent. They are part of a legally compulsory trading scheme. And I think the current proposals is actually to bring, prior to this, agriculture was only going to be voluntary. So I think there is going to be an opportunity for the voluntary market. There will be a proportion which could come from European farming. And I think the price at the moment is about 150 euros a ton, thereabouts. So again, that would also, so in terms of 2030, just to answer your question, yeah, it would hope it needs to be higher. And then also we're working with people in Europe, and one of those are getting income of 250 euros a ton. So look, I think that's probably a bit high at the moment, kind of 100 euros. And of course, as Bastiaan was explaining, if you're talking 5 tons per 10 centimeters, that's quite interesting in terms of income that you can obtain from this. Just also, you had the question about paludiculture farming. So in terms of the emissions, yeah, basically it depends obviously what crop you're growing. It's all moving in the right direction. And essentially the literature says, depending on what you're growing, it's going to be a 70 to 90% reduction in greenhouse gas emissions. And of course, that's there. They're raising the water table. And actually, depending on what you grow, so if you're looking at reeds, which is another one we're going to do in the next slide, we're going to have an expert over talking about reeds in our next farm event. And also bulrushes or cattails, they can sequester anything up to 15, 20 tons of dry matter per hectare. So, the opportunity there is that you can knock off those CO2 emissions. You can get that carbon money, hopefully around 100 euros a ton, which could be very significant. And then you can produce a product. And if that product then goes into building, which is what it can do, you may also get credits there as well. So that's why we talk about a stacked income opportunity from, doing different things with peatlands. So that's that. I also had a question just to me from one of the paludiculture farmers, Adrian. So I'll just check what his question was. Yeah, so he was asking about the set price and how much per ton. So as I said, yeah, the operating principle is about 100 euros a ton. So as Bastiaan says, 10 centimeters is five tons, 20. So if you're drained to 70 or 80 centimeters, and then there's also, as Bastiaan was mentioning, that cutoff point 40 below is business as usual. So there's an opportunity there to get a sizable income without actually changing any of your farming practices. But if you want to go higher, then that's also a possibility. And then also, how long is it going to take for a farmer to get the first carbon credit payments? Well, the standard is out since March. We're working on projects. So, I think the sooner we can get a project in the pipeline, the sooner we can get payments. But specifically what the standard requires is, again, as Bastiaan was explaining, it's all about water level with peat. So you need a 1 year's worth of water logging data logged. So the water level logged every hour for 1 year is your baseline. So let's say it's 70 centimeters below. And then when you do raise the water table, it's the difference that you'll be paid for. And again, as part of our current project, that's part of what we'll do. So if a farmer's interested, and it's not just the peat grassland, it could be the cutover or even bog. There's a lot of damaged bogs in the farms in the Midlands. We'll put those loggers in. So it's 1 per hectare is sufficient to give you the baseline. I think that's it on Adrian's questions. Again, he was just saying, as Bastiaan, it's the 10 centimeters. For peat grassland is 5 tons. For other types of peat habitats that a lot of farms have, the cutover might be less, maybe 2 to 3 tons, but that's still significant, particularly where you're not doing anything with that land anyway.
This is all going to come
Yeah.
up in the next webinar. So we're going to be talking
Yeah.
about 2 farms that we are currently working with and which have already re-wetted things. I'm going to use them as examples to discuss the habitats that they have right now, the water tables that they have right now. Sometimes I need to make a bit of a guesstimate, and then what could everything look like after re-wetting and how much uh, carbon or how much avoided emissions would that mean, and therefore how many carbon credits would that mean, and then combined with the size of the area we get to a total sum of what just raising the water table and changing the land use, because sometimes you have to change the land use, would mean financially. Now, just ahead of that meeting, it's I have to make some guesstimates, right? I cannot predict with 100% accuracy what the water table is going to be. It's also not something, a plan that's been fully laid out, and sometimes things are a little bit difficult because there's a plantation with the contract, so you can't actually do anything about that. But you know, I'm using all these kinds of landforms just to give you guys an idea of what it could look like and what different kinds of current land uses could yield if you would change them. So yeah, I highly recommend you get there. But just to answer your questions, you know, really quickly, changing on peat grassland, it's easy. 15 tons is easy. So 15 tons would be 1,500 euros, right? On cut over woodland, so if it's naturally regenerated woodland, I think around between 7 and 13 tons, just from the top of my head. If you have a bit of forest that's currently up for clear felling and not for replanting, there's a really big, I forget the number, but it's over 10 tons. And also, if there's any bare peat that you have lying around, bare peat is very, very bad for the environment. It emits a lot of CO2 simply because a lot of that peat erodes into the drains. So if you revegetate that, you're already making a huge impact. And yeah, you can get paid for that unless you've been cutting peat until recently, then no. But it takes a long time for vegetation to naturally come back to drained bare peat. So we see some around, and that's been like that for a good long while.
Very good. So any other questions? Sorry, Kayla, you do your thing there, yeah?